So today we're going to go into a new chapter, and the new chapter is called Light, okay, which is actually an extension. It's an extension of the chapter of waves, lah. Okay, but we're looking at a very specific wave. So previously we looked at the four phenomena. Okay, if you remember the four phenomena, we are looking at the four wave phenomena. The four wave phenomena is of course the first one that we learned was reflection. Okay, and then the second one is refraction, and then the third one is diffraction. Okay, and then the last one is interference. Okay, so these are the four lah. These are the four wave phenomena that we looked at in the previous class, in the previous chapter. Okay, but in this chapter, when we look at light, we are only looking specifically at two phenomena, which is reflection, and the second one is refraction. We're not really going to focus on this diffraction and interference. We are only going to look at these two next year, okay, in Form 5. And so I want to start off by reminding you that everything that you learn in Chapter 5 about reflection, refraction, especially these two, okay, will be very important in this chapter. We're going to look very specifically into this chapter, and we're going to begin by looking at the refraction of light. Okay, refraction. Now remember refraction. Refraction is the bending of waves. Okay, we change the direction by we bend the direction. Okay, the bending of waves, and the bending of waves happens because of the change in density. Okay, so the density of this one change, the density of the density of the material change lah. For example, if you go from shallow to deep water, okay, so the density of the water has changed. So when the density of the water changes, the refraction of waves happens. Okay, but in the case of light, okay, when we talk about density, we're talking about, let's say, for example, a light that is shining into a glass block. Okay, usually we are talking about is changing from air into glass. It's going from air into glass, okay, and then from glass into air. So when light moves from air into glass, it changes direction. And then when it moves from the glass to the air, it changes direction again. Okay. Another application that we see of this is in lenses. So the specs that you wear, okay, actually is an application of the refraction of light. Okay. So diagram 1 shows a pencil looking as if it is bent in a glass of water. I don't know if you've seen this before. Have you seen this like sort of magic trick before? Not really. It's not really a magic trick lah. Okay, but if you have a glass, okay, and then you put an arrow that is this way, right? Then when you pour water into the glass, you find that suddenly the arrow changes direction. Okay, I will send you a video of this later, but it is an application of refraction. Okay, so when refraction of light happens, the waves actually have to change direction. And that's why you see the arrow, it's not a magic trick actually, it's just refraction of light. The arrow actually, if it's pointing this way, when you pour in water, suddenly it will point this way. Okay, it will point the other way. So the same thing with this pencil in the water lah. Okay, so when the pencil is in the water, you find that there's this bit of pencil over here that seems to be bent. Okay, this part looks like it's bent, macam dia terbengkok lah. Is it really bent? No. It just looks to us as if it is bent. Okay. Another one, if let's say, or actually even if you go into the swimming pool, you will find that the swimming pool seems a bit shallower than normal. Okay. Objects inside the swimming pool. Okay, objects inside the swimming pool look as if they are nearer to the top than they actually are, which is actually not true lah. Okay, actually they are much deeper down, except that we can't really see that they are much deeper down. Okay, because refraction of light, and we'll soon see this lah. Okay, how does refraction work? So that when we see the fish, actually we see it here, but actually the fish is over here. Okay, so why does this happen this way lah? Okay, that is what we're going to look at today. All right, so light travels in a straight line through transparent materials such as air, water, and glass. Actually, it travels in a straight line. But if light passes through two different materials of different, okay, this is a word that I want you to underline and I want you to highlight, okay? And this is a very specific word that has to do with light only. Okay, when we're talking about, so remember in chapter 5, we talk about density, right? When we talk about density, we're talking about, uh, when we talk about density, we're talking about, sorry, we're talking about density of materials, lah, okay, as the waves pass through. But for light, we use a slightly different term, okay, which we call optical density. Okay, this is very specific for light. Okay, so when light passes through two materials of different optical densities, it will change direction. And this is what we call the refraction of light. Okay, so let's talk about the I don't know, the meaning of refraction of light. So refraction of light is a phenomenon, okay, just like there are four phenomena: reflection, refraction, diffraction, and interference. So refraction of light is a phenomenon where the direction of the light changes. Okay, so these are the key words. Direction changes when it travels through two materials of different optical densities. So this is the definition. The changing of the direction of a light, okay, when it passes through materials with different optical densities. Okay, for example, this is a less optical dense, this is more optical dense. You find that it is bent, like this. Okay, now why does the light change direction? Okay, so this is the answer to this now. Why does the light change direction? It is because there is a change of speed of light when it passes from one medium into another. Okay. The best way, the best way to think about this, okay, the best way to think about this is to think of the light that is going, or sorry, an object that is going through traffic. Okay, let's say in a traffic jam, okay, in a traffic jam, if let's say there's a lot of cars, it's very easy for the motorcycle to pass through all the cars because, sorry, if there's very little cars, sorry, if there's very little cars, okay, then it's very easy for the motorcycle to zip past through. So the motorcycle will be able to move much faster. But if there's a lot of cars, okay, if there's a lot of cars, it's very difficult for the motorcycle to move very fast. Okay, it's very difficult for a motorcycle to move very fast because there's so many cars in there. Okay, so in the same way, we think of this one, we think of it as optically dense and less optically dense. Okay, so light is refracted because of the change of velocity, change of speed. Okay, light travels more slowly in glass than in air because glass is more optically dense and air is less optically dense. Okay, think about it in the same situation. So more optically dense, okay, more optically dense is like the situation where there are more cars. Okay? More cars means the motorcycle have to move slower. Okay, that's why light travels more slowly. If it is less optically dense, means you're in a situation where there are less cars on the road. If there are less cars on the road, then the motorcycle can very easily move very fast. Okay, can definitely move much faster. Okay, and also, this is also another thing because we have to talk about the change in direction also, because that's what refraction is, right? A refraction is the change in direction. Think about the situation where there are more cars. Okay, if you have ever been in a traffic jam, you will know this lah. Whenever there are more cars, okay, wherever there are more cars, so the motorcycle has to go slower, and then it tends to it tends to go in between the cars, like all over the place lah. Whereas there's less car, the 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 motorcycle can easily go straight. Okay, it doesn't have to really change direction a lot. So more cars means more change in direction. Okay, this one, when I say more, I will talk about this in a little while. This is less change in direction. I'm not saying that there's less, but uh, I will talk, sorry, I'll talk about this in a little while. But this is the idea. The idea is this. When refraction happens, the light is changing speed. Okay, it is moving faster or moving slower. And as it moves faster and it moves slower, it also has to change in direction. Okay, so as it moves slower, there will be more change in direction. As it moves faster, there'll be less change in direction. The light can just go straight. Sorry, the motorcycle can just, go straight like that. So when a light beam passes from air into glass, the speed of light decreases because air is less optically dense than glass. Glass is very dense. Dia sangat tumpat. So obviously glass is going to, have the light is going to travel slower in glass because of the words optically dense. It's more optically dense. Okay, and when it moves slower, it will bend. It will bend even more. Okay, so sorry. So this is in the same case lah. So you find that, okay, so in this case, we will talk about this drawing in the next section in this activity one. Let's take a look at this. Okay, so let's say you have a bongkah kaca, you have a glass block put on a piece of white paper. Okay, now when you aim a light at the glass block, so let's say this is the glass block. This is the glass block. Okay, when you aim the light at a certain point in the glass block, okay, this ray is called the incident ray. Okay, this ray is called the incident ray. And when you see the light inside the glass block, okay, after it passes through the glass block, this ray is called the refracted ray. Okay, dalam bahasa Melayu, this is tuju, okay, sinar tuju, and this is sinar biasan. Okay, dia sudah terbias, already refracted. Okay, so this is what we call the refracted ray. Now, the point, okay, the point where the incident ray becomes the refracted ray, if we draw a normal line. When I say normal line means it is 90 degrees to the border. Okay, this is the border, the border line where the glass block is. If I draw a normal line, 90 degrees, okay, I'm going to call this a normal line. Now, the angle between the incident ray and the normal is called the angle of incidence. The angle between the refracted ray and the normal is called the angle of refraction. Okay, so there are many things in here that we kind of need to know. 5 things altogether. You need to know what is the incident ray. You need to know what is the refracted ray. You need to know what is the angle of incidence. And you need to know what's the angle of refraction. And remember that the angle of incidence and the angle of refraction must touch the normal. Okay, it cannot be, this is not, okay, this is not the incident ray because it's not touching the normal. It must touch the normal. This is not the refracted ray, okay, because it is not touching the normal. But if I give you this angle, okay, for example, let's say I say this is 50 degrees. Can you tell me how much is the degree of I? What is the angle of I? If this is 50, how much is I? Anybody? Okay, it will be 40 degrees. Okay, because again, the normal is a 90-degree angle. So everything is 90-degree angle. Okay, so you need to know that relationship. But the incident angle and the refracted angle must be the angle that is touching the normal. Okay, I cannot stress this enough because every year I teach this, I'm sure that some people will get this wrong. Okay, sure they will think, oh, this 50 since it's given 50 already. Okay, come on. Incident angle always touch the normal. Okay, so you can fill this in the table in your module. Okay, so the incident ray is the light ray that is directed to the boundary. Refracted ray is the ray that is refracted after it passes through the glass block. The normal line is a line at right angle, okay, or 90 degrees to the boundary. Angle of incidence is between the incident ray and the normal line. Okay, and the angle of refraction is the angle between the refracted ray and the normal line. Okay, so light ray travels much slower in a denser medium. This is a very important statement. So when light ray travels from one medium to another, okay, the speed will change. The change of speed of light causes the change of its direction, okay, which is what we want to talk about in this. So remember, the speed of light now really depends on the optical density. Okay, again, you see this word, optical density. The bigger the optical density, the slower the light will travel inside, okay, that material. So let's take a look at this. So light travels from a less dense medium to a denser medium. Okay, so what you're going to see is, you're going to see this one over here. Okay, so copy this down. So this is the incident ray, okay, and this is the refracted ray. Notice the size of the incident ray and the refracted ray in this slide. Okay. Now, how do you explain the direction of the refracted ray? Okay, and this is how we explain it. Okay, so we say that the direction of the refracted ray is towards the normal line. Okay, maksudnya it is getting closer to the normal line. Okay, and when you compare the angle of I and the angle of R, yeah, you kind of need to draw this in your activity book, I think. Can you do that? Yeah. So make sure that, sorry, this is question A. So make sure when you draw, you make sure that this line over here, the second line over here, the angle over here is smaller than the angle of I. Okay, so I is always bigger than R. Okay, so state the change of speed of light after it is refracted. When it is refracted, because it is going into the glass, right? Okay, the speed of light will decrease after refraction. So this brings to us a few important points that we need to talk about here. Okay, number one is that when you're going from less optically dense to sorry, hold on, to more optically dense. Okay, less optically dense to more optically dense. For example, you're going from air into glass. Okay, a few things happen. Number one, it will move, the refracted ray will move towards the normal line. It will become nearer to the normal line. Number two, the angle of I is bigger than the angle of R. And number three, the speed of light decreases inside the glass. Okay, remember the analogy of the optically dense. Less car, more car. More car means the motorcycle moves slowly. Okay, so all this is connected now. This is from less optically dense to more optically dense. Okay, the second one is the opposite. You're going from more optically dense to less optically dense. So if the less to more is towards the normal line, how would you say is the more to less? It will be the opposite lah. Okay, you will find that the angle of I over here and this angle of R, everything is terbalik. If less to more is towards normal line, okay, more to less, it will be away from the normal line. Okay, so highlight this. Okay, how do you mention the direction of the refracted ray? It's either towards normal line or away from normal line. Okay, in terms of the angle I and R, this one, I think if you compare, you can see this very clearly lah. I is definitely much smaller than R. Look at the angle of R, very big. Okay, I is definitely much smaller than R. And so why is it moving away from the normal line? In terms of the speed of light, since it is moving in a less dense medium, think of the motorcycle and the traffic again. Less dense means less car. Less car means the motor can move faster. Okay, so the speed of light increases after refraction. Okay, so these are very fundamental differences when you go from air into glass or glass into air. Less dense to more dense, or in this case, this is more optically dense going into less optically dense. So you need to know this difference. Okay, you need to know which one is more optically dense, which one is less optically dense. But when it's going from more to less, this is what's going to happen. If it is going from less to more, this is what's going to happen. Okay, it's going to move towards the normal line. The incident angle is going to be bigger. The speed of light is going to decrease. Okay, because it's more optically dense, more cars. Okay, C is if the light, if the light is parallel to the normal line, means it is at the same line as the normal line, okay, like this. Okay, and so we find that if it is in the same line as the normal line, the refracted ray is also going to be parallel with the normal line. Okay, that's the important thing. Okay, but the thing is, even though it is parallel with the normal line, the speed of the light will still decrease because you cannot change this rule. If it is moving from a less optically dense, okay, to a more optically dense medium, the speed of light is going to decrease, definitely. Okay? Just that the direction really depends on whether it is the direction depends on whether it is away, whether it is at the angle with the incident angle, or whether it is uh, totally, celari or parallel with the normal line. Okay, is that okay, everyone? Can I continue?
Okay.
Okay. All right. So the next thing I said is that we have to know what is this thing called the refractive index. Okay, it is a number that is represented by the letter of n. Okay. Now the refractive index determines the degree to which the light bends when traveling from vacuum to a medium. The bigger the refractive index, okay, the bigger your refractive index, okay, the more your light will bend. Okay? The bigger the refractive index, the more the light will bend. So for example, if you're shining a light from air into water, for example, or if you're shining a light from air into glass, you find that the glass, the light inside the glass, right, will bend a lot more. Why? Because inside the glass, the speed of the light inside the glass is very slow compared to if it is in water or in oil. Okay. Yes, it will slow down, definitely. When it's going from air into water or air into glass, both of it will slow down. But the one in glass slows down more. Okay. Why? Because glass is more optically dense. Definitely more optically dense than water, for example. Okay. Again, remember again the analogy of the motorcycle that I said just now. More optically dense means got more cars on the road. More cars on the road means the motorcycle has to go much slower. Okay, and when that happens, the light will bend even more. Okay, because it is going slower. So this is what this refractive index means. So this number very important. Okay, the bigger the refractive index, the more the light will bend. So how do you count refractive index? So this is cara number satu. The way number one is you calculate the speed of light in vacuum divided by the speed of light in the medium. Medium can be glass air no, sorry, glass water oil plastic Okay, all this is medium But speed of light in a vacuum is a constant. The speed of light in vacuum is 3 times 10 to the power of 8 meters per second. Okay, it's 300 million meters per second. Okay, that is the speed of light. So this is the first way to calculate the refractive index. Okay, so just to remind you, C is 3 times 10 to the power of This is a constant lah. Okay, don't have to worry about this. All right. The second way, the refractive index has no unit. Okay, it is just an indication of light bending ability as the ray of light enters from its surface from the air. Okay, so for example, as I said just now, air, water, glass, and diamond. Look at the refractive index. In diamond, the refractive index is very high. Air, air is basically everywhere lah. So air definitely is 1 lah. Okay, look at the speed of light. Okay, the speed of light in diamond is very slow, 1.2 times 10 to the power 8. Compared to water, compared to glass, definitely compared to air. Okay, very low speed of light, very high refractive index. Okay, this is a very important relationship. The bigger the refractive index, the smaller the speed of light inside that medium. Okay, that's why everybody likes diamonds. Because the speed of light is slow, so that's why we can see it blink a lot more. Imagine if it's glass. Glass is 2 times 10 to the power 8. It doesn't blink so much. Because the speed of light is faster inside glass. But in diamond, it's very slow because it's very optically dense. So since the speed of light is very slow, that's why we see all this blink, okay, inside the diamond. Okay, so diamond has the biggest optical density. So the refractive index of N is the biggest. The light bends more in diamond rather than in glass and in perspex. Take a look at the angle of refraction. Okay, so when you see perspex is like plastic. It's a plastic lah. It's a kind of plastic lah. So look at all the incident angle is the same, 50, 50, 50. But look at the refracted angle. The refracted angle is 24.9 for diamond. Okay. So what does this mean? If the refractive angle is small, the smaller the refractive angle, okay, the more it is bent. Okay, they are more bent lah. Sorry, did I say more bent? Less bent. Okay, because it is. Wait. More bent. Sorry. Because it is slower. Yes. Okay. Hold on now. I don't really like this word more bend, less bend lah. But we find that the bending is a lot more lah. Okay, compared to the original. Look at the original. If light travels in a straight line, it will be like this. Okay, but there's a lot more bend over here compared to if I do this. Look at this. Right? The bend over here in the diamond is more than the glass, and definitely more than the perspex. Look at this angle is the smallest. Right? So the smaller the refractive angle, the smaller the refractive angle, the more the light will bend. Okay, so the light bends more in diamond rather than in glass that in perspex because of the biggest refractive index. N 是最大的. N is the biggest, okay, in diamond. Okay, that's why the bend is more. Okay, and when we say bend is more means the refractive angle is smaller lah. Okay, so all these things are are kind of like, oh, okay. Yeah, a lot of things that we have to think about in this chapter. Okay, so the law of refraction says this. Number one, the incident ray, okay, and the refracted ray and the normal line all lie on the same plane. This is the law number one. There's an empty space underneath this Snell's law right inside your workbook. I want you to copy this, okay, in the empty space over there. Okay, so the law of refraction says these two things. The incident ray, the refracted ray, and the normal line all lie on the same plane. Okay, same plane means they are all on the same surface. It's not this is the incident ray, this is the refracted ray, and then this is the normal line. No, it's all in the same place. It's all on the paper. Okay, if we put it on the paper. Okay. The second law says that the value of sine I divided by sine R, okay, is a constant. Okay, but there is a condition to this. Ada syarat untuk inilah. The I, okay, the incident angle must be in the vacuum or in the air. Okay, the incident angle must be in the vacuum or in the air. And I think that's a very important thing, okay, that we need to remember lah, okay, from this. And this is the formula. This is the second formula for refractive index. Remember the first formula? The first one is speed of light in vacuum divided by speed of light in medium. Okay, in the glass line, in the diamond line, in the perspex. So this is the second one. The second way to calculate refractive index is sine I over sine R. Okay, remember once again, I is the incident angle, okay, and R is the refracted, okay, angle. That's I and that's R. Okay. Now, in the space where you are required to write the Snell's law, okay, you can write this lah. Okay, this formula. Okay, n1 sine theta 1 equals to n2 sine theta 2. So the refractive index in medium 1 times sine of the angle in theta 1 is equals to the n2, the refractive index of medium 2, and theta 2. Okay, and if we put what we will find is n2 over n1 equals to sine theta 1 over sine theta 2. Okay, let's do a short exercise for this. Okay, while we're this one. So let's say this is 50 degrees. Okay, and my n1, my n1 over here is 1.00. Okay, let's say it's 1.00. Okay, so let's say my n2 over here is 2.42. Okay, my question to you is, what is the value of theta 2? Okay, can you calculate that now? Substitute either in this formula or this formula, doesn't matter. Whichever one you want to use also can. But you substitute correctly lah. Okay, give me the angle of theta 2. Okay, so he substituted in here lah. 1 times sine 50. Okay, so 1 times sine 50 equals to 2.42 times sine theta 2. Okay, then after that, when you pin down this 2.42, you will get sine theta 2, theta 2 equals to, how much is this? You get 0.3165 bahkan. Okay, so how do you get this theta 2? How do you get 18.65? What must you do? Okay, you press shift sign because it is sine theta over 2, right? So you pin down the sign over, you get shift sign 0.3165, you get 18.45, sorry. Okay, 18.45. Okay, so for those of you who are not sure about this, just maybe you can write a reminder over here lah. Okay, if want to find angle, if want to find angle, must use shift sign. Okay, must use shift sign in order for you to find the angle. Okay, just to remind yourself. Right, good. So let's take a look at what this means. This means that when medium 1 is air, medium 2 is n2 equals to n, okay, we can actually do any calculation. Okay, but actually from here, we can actually get this formula. Okay, but it's not very important for us to know this. We just have to do that Snell's law, okay, started with this, Snell's law started with this formula, okay, and ends with this formula. Okay, so this is the third way to calculate the refractive index. Okay, n1 sine 1 equals to n2 sine 2. Okay, the third way to calculate the refractive index. So let's do a short recap. How to calculate refractive index. Okay, n equals to sine I over sine R. N equals to the speed of light in the vacuum or air over the speed of light in the medium. Okay, now remember that if you're going to use sine I over sine R, okay, you need to make sure that I, okay, the angle of I is in the air or vacuum. Okay? You cannot do sine I over sine R and then the I is in the glass or in the water or in the perspex. No. Okay, this one comes with a condition, very important condition. Okay, I must be in the air because when we calculate using the speed of light, the on top one is in the air. Okay, we don't use the one in the medium. Okay, and remember the third one is n1 sine theta 1 equals to n2 sine theta 2. Okay, so there are kind of three formulas that we have to think about today, or at least in this subtopic, okay, which we will look at. Okay, let's take a look at the next page. Okay, I want to kind of do this experiment, okay, with you all, but I need you to do this first, and then on Wednesday, we will discuss the results of this experiment. Okay, I want you to take a look at this setup. Okay, take a look at this setup and everything. Take a look at the procedure. Okay, just take a look at it first. Okay, you may not understand it, but don't worry, just take a look at it. But I want you to tell me, think about it for a while. Tell me what is the hypothesis, what is the manipulated variable, responding, and fixed variable. Okay, let's start with this first. Okay, what do you think is the hypothesis of this experiment? The aim is to investigate the relationship between the angle of incidence and the angle of refraction. Okay, that's the aim of this experiment. So tell me what is the hypothesis, the manipulated, the responding, and the fixed variable. Okay, I'm going to give you 3 minutes to think about this. Write down your answer first. Okay, so everything comes from the inference. The two important thing is the thing that we want to find the relationship in. So in this case, we want to find the relationship between the angle of incidence and the angle of refraction. Okay, and I think that Nikki has kind of gotten the idea correct. The angle of incidence is the manipulated variable, and the angle of refraction is the responding variable. When you read through the Langkah, sorry, let me see if the Langkah is there. Yeah, the Langkah is there. When you read through the Langkah, you'll find that what we are changing is the angle of incidence. Okay, what we're changing, this is the manipulated variable. And what we're reading is the responding variable, the refraction angle. So how we write inference, okay, let's recap this again. So the template for writing inference is the responding variable, okay, depends on, okay, the manipulated variable. Or if you want to use Bernardine's words, also can, okay, is influenced by the manipulated variable. 也是可以一样啦, okay, it's the same thing. So you can say angle of refraction, okay, depends on angle of incidence. Okay, this is how we will write the inference. Okay, which I think actually Bernardine kind of has the idea over there. It's just that we're not using the, the aim. Okay, the aim should actually help us, okay, to write the inference. And the next one is, of course, to write the hypothesis. Actually, it's the bigger the incident angle, the bigger the refracted angle. Okay, when I increase this, you're going to find that this refracted angle is also going to increase. Okay, I know that, I probably think that why Vion said the bigger the incident angle, the smaller the refracted angle, is because you're just comparing these two. But actually, we're not. We're comparing one incident angle to the next incident angle to the next incident angle. Okay, which is okay. Okay, no problem. Okay, but this is actually the relationship, okay, between the incident angle and the refracted angle. When you increase the incident angle, the refracted angle is also going to increase. Okay, although every situation, the incident angle is always going to be bigger than the refracted angle. That's true, because you're moving from air into glass. Okay. Now, the manipulated variable, Nikki, is not the ray, it's the angle. Angle of incidence, angle of refraction. Okay, The fixed variable is the density of the glass block. Okay. This is a this is probably the thing that we're not really sure about. Okay, the density of the glass block is the fixed variable for this, because we are always using the same glass block. We don't change the glass block. What we are changing is the angle of incidence. Okay, and what we're reading is the angle of refraction. So the thing that remains the same is actually the density of the glass block. Okay, so what I would like you to do, okay, for your classwork today, which I want you to complete before our Wednesday's class, because if you're not going to complete this before Wednesday's class, then you don't come for class. Okay, otherwise it's going to be a waste of time for you and also a waste of time for me. So I want you to go to, I'm going to share this, okay, this simulation with you. Okay, and when you get into this simulation, you click on intro lah. Okay, you click intro. So you're gonna get this ray. Okay, set this as ray. Okay, so that when you turn it on, you will get a red color light lah. Okay. Yes, you can do it as wave also if you want lah, but it's going to be such a border, so ray is easier. Okay, then over here is the protractor. Okay, so you can set the protractor over here. And then you take a look at the table inside your activity book. It starts with the I equals to 30, right? Okay, so remember, this is the I. So you move this position into 30 degrees. Okay, and then you read the angle of refraction over here from 0 to how much. Okay, it's pretty easy, but make sure that this is air and glass. Okay, there are many different ones here. There's water lah, there is mystery A lah, there is mystery B lah, I don't want. Okay, we just want air and glass. We follow exactly like the table over here lah. Okay, we follow exactly like the table over there. So once you have done this experiment, you've gotten the values of R. Okay, what I want you to do is, I want you to complete the table and I want you to plot the graph. Okay, do you see the graph that they ask you to plot? Plot the graph of sine I against sine R. Okay, so the experiment actually is very fast one. Okay, shouldn't take too long. You just make sure that one is air, one is glass. You do this one, complete the table, plot the graph, okay, and then you plot the graph over here. Okay, if you don't like this graph paper, you can use your own graph paper, but I want everyone to take a photo of the graph, take a photo of your graph, okay, and post it into the Padlet, which I will share with you after this, okay. And just like today, only people who have done the graph, I will allow you to join in the next class. Because if you're not going to bother to finish the work that I asked you to do, I don't think you should come for the next class. Okay, so, and I don't think it's very difficult to do this. You just have to calculate the values, conduct the experiment, draw the graph. I'm not even asking you to answer the questions. I'm just asking you to draw the graph. Okay, so that in the next class, we don't waste time waiting for you to draw the graph.